Somewhere in the constellation Canes Venatici, 463 light-years from Earth, a planet called Puli dances around its star in a rhythm just slightly off. At first glance, there's nothing particularly special about Puli. It's a sub-Saturn world, larger than Neptune, smaller than Saturn, orbiting a star called HATP-12, also known by a more charming name, Komondor. Both the planet and its star were named after dog breeds, a nod to their place in the hunting dogs constellation. But Puli is special, not because of what we see, but because of when we see it. This planet, discovered via the transit method, periodically crosses in front of its host star, causing tiny dips in the star's light. These dips, or transits, are the bread and butter of modern exoplanet science. They allow us to measure size, orbit, and sometimes even atmospheric composition. But Puli's transits weren't as predictable as they should be. In a perfect world, Puli would pass in front of Komondor like clockwork, each orbit a carbon copy of the last. But that's not what astronomers found. Instead, Puli was early, then it was late, then it was early again. This phenomenon, known as transit timing variations, or TTVS, is like a cosmic stutter, a hiccup in the harmony. And while a difference of a couple minutes may seem small, in the realm of orbital mechanics, it's a glaring alarm. A team of researchers led by Kavya Parthasarathi at National Tsinghua University in Taiwan decided to find out why. They analyzed 46 light curves, records of Puli's transits collected over years by telescopes in the ground and in space. Some of this data had never been studied in detail. Some came from the Transiting Exoplanet Survey Satellite, or TESS, one of our most prolific planet hunters. Across those 46 transits, one pattern kept emerging. Puli's timing varied by up to 156 seconds, more than 2.5 minutes. Not randomly, not chaotically, but consistently. Like something else was tugging on it, nudging it forward or holding it back. Something invisible, something gravitational. But before jumping to conclusions, the researchers needed to rule out the ordinary. They tested 4 different models to explain the variation. The first was a linear model, a straight, unchanging orbit. That one fell apart quickly. The transit times were clearly inconsistent. The second was orbital decay. Perhaps Puli was spiraling inward toward Komondor, gradually shortening its orbit, but that would have produced a steady change in transit times in one direction. That wasn't what the data showed. Then came the apsidal model, considering whether Puli's orbit might be slightly elliptical and precessing like a slow wobble. That model fit better, but still not quite right. And finally, they tested a sinusoidal model, one that suggests Puli is being pulled by the gravity of a second unseen planet. This was the model that worked. It matched the amplitude of the timing variations. It matched the rhythm. It explained the dance. According to the sinusoidal model, there's another planet, smaller than Jupiter, perhaps just 2% of its mass, orbiting nearby every 6.24 days. We haven't seen it directly, but its presence is written into Puli's orbit like fingerprints in the sand. This discovery wasn't made through a telescope. It was made through timing, through patience, through 46 careful observations, through mathematics and models, and a relentless refusal to ignore a 2.6-minute irregularity. And it may be just the beginning. Because the more we collect this kind of data, the more we look at not just where planets are, but when they are, we might find a universe filled with unseen companions, writing gravitational signatures into the orbits of the worlds we thought we already knew. In astronomy, light is often the main tool. We use it to image distant galaxies, to study the surfaces of alien worlds, and to probe the atmospheres of planets we'll never visit. But sometimes, what matters most isn't light, it's time. Transit timing variations are one of the most delicate instruments in the astronomer's toolkit. They don't show us a planet directly. They show us its influence, its effect on another world's orbit. And in that effect, we find evidence of something more. To understand why this matters, let's return to the basics. Planets orbit stars because of gravity. The more massive the star, the more tightly it holds its planets. The farther out a planet is, the longer it takes to complete one trip. This relationship is governed by Kepler's laws of planetary motion, rules written more than 400 years ago and still accurate enough to send spacecraft across billions of kilometers of space. When we find a planet via the transit method, we measure how often it crosses in front of its star. If those transits occur at perfectly regular intervals, say every 3.213 days, we can calculate the shape and size of the orbit with high precision. But if those times shift, if the planet is early or late, we know that something is perturbing its path. Those shifts are what TTVs capture. In the case of Puli, the variation reached over 2 minutes. For comparison, many TTVs detected in other exoplanet systems are measured in seconds. The size of the shift in Puli's case made it more likely to be caused by a nearby companion planet, rather than stellar noise or instrumental error. And here's where the beauty of physics comes in. By fitting those timing shifts to mathematical models, astronomers can simulate the gravitational influence of hypothetical companion planets. They can adjust variables like mass, distance, orbital eccentricity, and period to see what configuration best reproduces the observed data. In other words, they build an invisible solar system, one that explains what we see. This process is similar to how Neptune was discovered in our own solar system. In the 1800s, astronomers noticed that Uranus didn't move quite as expected. By studying the deviations and applying Newtonian physics, they predicted where another planet must be. When they looked through telescopes, there it was. Neptune, right where the math said it would be. Today, we're doing the same thing, except with no hope of ever seeing the companion directly. Instead, we infer, we model, we trust the precision of time. In the case of Puli, the sinusoidal TTV model suggested a gravitational tug from a neighboring world in a resonant orbit. That planet's pull causes Puli to speed up or slow down just enough to alter the timing of its transits. The effect is subtle, but measurable. And that's the heart of this technique. We don't watch the planet, we watch the shadow it casts. And we measure how the timing of that shadow changes. From that, we learn not just about Puli, but about the other world that must be there, dark, cold, and hidden. The model predicts that this unseen companion has a mass around 2% that of Jupiter. That's roughly 6 Earth masses, somewhere between a super-Earth and a mini-Neptune. Too small and dim to detect with current direct imaging techniques, but large enough to nudge Puli off its schedule. Its orbit is 6.24 days, meaning it circles Commodore almost twice for every one orbit of Puli. This kind of near resonance is known to amplify gravitational interactions, and it fits neatly into the data. But to confirm this, the researchers needed to rule out other possibilities. Could the host star, Commodore, be the culprit? Some mechanisms, like changes in the star's magnetic activity or shape, can create small shifts in the timing of a planet's transits. This is called the Applegate mechanism. But when the authors ran the math, the maximum timing variation it could account for was only 0.4 seconds. Puli was shifting by 156. That left only one plausible explanation: gravity, another planet, one we haven't seen, but whose presence is written in Puli's timing. It's a quiet kind of discovery. There's no photograph, no dramatic image, just numbers. But in those numbers lies a profound revelation. The orbit of one world can whisper the existence of another. And that whisper just became a shout. The science of transit timing variations may seem like a recent innovation, but its foundations go back centuries. At its core, TTV analysis is an extension of celestial mechanics, a tradition dating back to Johannes Kepler, Isaac Newton, and Joseph Louis Lagrange. Long before we knew of any planets beyond our solar system, astronomers noticed that the orbits of known bodies weren't always perfectly predictable. Tiny deviations in Mercury's orbit hinted at problems in Newtonian gravity, problems that would later help inspire Einstein's general relativity. And long before Neptune was seen through a telescope, it was felt, its tug on Uranus calculated before it was ever visualized. This is the tradition into which TTV research falls, using timing and motion to reveal the hidden. In Puli's case, the research team tested 4 different models to explain the TTV data. Each model reflected a different physical process that could cause the observed deviations in the planet's transit schedule. Model 1, the linear orbit. This is the default assumption that the planet moves in a perfectly periodic, stable orbit with no significant interactions or changes. Under this model, every transit occurs exactly when predicted, following a straight line through time. But Puli broke that assumption. The transit times varied by more than 2 minutes, far too much to be noise or measurement error. The linear model failed almost immediately. Model 2, orbital decay. This model considers whether the planet is slowly spiraling inward, its orbit decaying due to tidal forces or other effects. If true, Puli's transits would steadily shift in one direction over time, either earlier or later with each orbit. But the data didn't match that pattern. The variations weren't monotonic, they were oscillatory. That meant something else was causing the fluctuation. Model 3, apsidal precession. Next came the apsidal model, which assumes the planet's orbit isn't a perfect circle, but a slightly stretched ellipse, and that the ellipse itself is slowly rotating. This phenomenon, known as apsidal precession, can change the apparent timing of a transit depending on where the planet is in its orbit when it passes in front of the star. This model fit the data better than the previous two, but it still didn't match the full pattern of the TTVs. The deviations were too regular, too rhythmic, to be explained by orbital wobble alone. Model 4, the sinusoidal companion. Finally, the team tested a sinusoidal model, one that assumed the presence of an unseen companion planet pulling on Puli gravitationally. This model predicted a repeating wave-like pattern in the transit timing shifts caused by the gravitational influence of a neighboring world in orbital resonance. And this model fit perfectly. It explained the 2.6-minute amplitude in the TLVs. It matched the frequency of the variations. It reproduced the entire data set with a remarkable precision. It told a story that the other models couldn't, that Puli was being pulled gently but consistently by something we hadn't seen. This wasn't just a good fit. It was the kind of fit that gives astronomers confidence. It wasn't proof, not in the strictest sense, but it was the best explanation we had. And it's not the first time this technique has worked. Over the last decade, dozens of exoplanets have been detected via TTVs. NASA's Kepler mission, in particular, uncovered dozens of multi-planet systems this way. Planets that were too small or too faint to detect directly, but whose gravitational pull was evident in the transit timing of their neighbors. One of the most famous cases is the Kepler-19 system. Astronomers noticed that the known planet, Kepler-19b, had irregular transit times. The variations were so regular and precise that they predicted a second planet, Kepler-19c, one that had never been seen. Eventually, radial velocity measurements confirmed its presence. The TTVs had told the truth. TTVs have also been used to measure planetary masses, determine eccentricities, and even infer whether planets are in orbital resonance, locked into rhythmic relationships that shape their evolution. In some cases, TTVs have revealed Earth-sized planets orbiting faint red dwarfs, planets that would otherwise be lost in the noise. In others, they've helped identify systems on the edge of chaos, where the orbits are so delicately balanced that a tiny change could trigger long-term instability. What makes TTVs so powerful is that they don't require direct imaging, high-contrast spectroscopy, or massive ground-based telescopes. All they need is time, patience, and precision. The downside, they require long-term observation, dozens of transits, years of data, and robust models that can disentangle overlapping gravitational effects. But the reward is worth it. In the case of Puli, the data spanned years, 46 separate transits observed from multiple platforms, some from ground-based observatories, others from TESS. This R, the discovery of a companion planet tugging at Puli, is not just a niche curiosity. It's a window into how planetary systems form, evolve, and sometimes reveal secrets only after years of observation. The Commodore system is, in many ways, a microcosm of something larger. It's not just about one planet nudging another slightly off schedule. It's about the possibility that our understanding of planetary architecture is still unfolding, and that timing anomalies may hold the key to rewriting it. Let's start with the architecture itself. The presence of a second planet, especially one in a near-resonant orbit, tells us that the Commodore system is dynamically complex. Puli and its hidden neighbor likely formed together, or at least migrated into their current configuration together. Their interaction suggests that the system has been gravitationally stable for a long time, but not without subtle interactions. Orbital resonance, where planets influence each other's orbits through rhythmic gravitational tugs, is one of the most powerful forces in shaping planetary systems. In our own solar system, Jupiter's gravity has trapped several of its moons in resonant orbits, causing them to stretch and flex under tidal forces, generating internal heat. The same principle might apply in exoplanet systems, but we've only just begun to uncover it. The fact that Puli's transits vary in a sinusoidal pattern means that its companion isn't just present, it's locked in a gravitational dance. Their orbits likely interact in a stable, repeating rhythm that has persisted for thousands, maybe millions of years. Why is that important? Because it gives us a laboratory. Most exoplanetary systems we study are snapshots. A few transits, a couple of radial velocity curves, and we move on. But when we find systems with TTVs like Puli's, we gain access to a dynamic data set, one that evolves over time, one that lets us study the gravitational choreography of alien worlds in real time. The implications go even further. This discovery suggests that many planetary systems, perhaps most, might contain hidden worlds, planets we've missed because they don't transit or because their signals are buried in the noise. But their presence is real, and their influence detectable through the timing of brighter, more visible companions. And that leads to a provocative question. Just how many complete exoplanet systems have we misunderstood? It's possible that many of the hot Jupiters, sub-Saturns, and many Neptunes we've cataloged over the past 2 decades are not alone. Their orbits may be subtly perturbed by smaller siblings, moons, Trojans, co-orbitals, or even massive, faraway giants we've yet to detect. Puli's timing variability acts like a flare, a signal that the system is more than it seems. And as more precise space missions collect data, missions like Plato and the upcoming Nancy Grace Roman Space Telescope will be able to extend this kind of analysis to hundreds, even thousands of systems. But it's not just about discovery. It's about testing theory. Planetary formation models make predictions about how planets should settle into orbits, how often they interact, and what configurations are stable. By studying TTVs, we get to see those interactions in action. We get to test whether our theories match the real universe or whether something deeper is going on. In some cases, TTVs have revealed instability, planets on the edge of resonance, systems close to chaotic breakdown. In others, we've seen beautifully tuned arrangements that suggest planetary migration, damping, and long-term equilibrium. With Puli, we see the signature of balance. Its companion, just 2% the mass of Jupiter, is enough to shift transits by a couple minutes, but not enough to destabilize the orbit. This balance suggests that the two planets may have migrated together during their early history, caught in resonance by the disk of gas and dust that once surrounded Commodore. That disk is long gone, but the rhythm remains. This is why the TTV discovery is so powerful. It shows us process, not just position. It reveals history, motion, interaction, and it forces us to ask, how many other exoplanets are being pulled by invisible hands? We're entering a new era in which the absence of evidence is no longer evidence of absence. We don't need to see a planet to know it's there. If it has mass, it has gravity. If it has gravity, it leaves a mark. And timing, perhaps more than light, is the language of that mark. Every shift in transit timing is a word. Every oscillation is a sentence. Every model we build is an attempt to read that message and translate it into the physics of worlds we may never directly observe, but we can still know they exist, because Puli told us. And if this system has something to hide, others probably do too. Science is sometimes thought of as a pursuit of light. Telescopes gather photons from distant stars. Spectrometers break those photons into rainbows of chemical information. Cameras record the reflections of cosmic history, frame by frame, from galaxies that died billions of years ago. But the discovery of Puli's companion wasn't about light, it was about timing. A planet passed in front of its star a few minutes early, then a few minutes late, then right on time. That pattern, subtle and almost imperceptible, told us everything. We didn't see the second planet. We felt it. This marks a shift in how we discover new worlds, not through brightness or color, but through motion, not through images, but through models, not by capturing light, but by noticing its delay. And as the tools of astronomy evolve, so too will our ability to read these signs. The future of transit timing variation research lies not only in better telescopes, but in better analysis, faster algorithms, deeper statistical modeling, and eventually, artificial intelligence. Already, astronomers are training neural networks to detect subtle, low-amplitude variations in transit timing that might escape traditional human review. These models can ingest thousands of light curves, simulate millions of orbital combinations, and identify gravitational signals that would take human teams years to analyze. The combination of high-precision instruments and AI-driven analysis may reveal thousands of new planets, not by direct observation, but by the trails they leave in time. Imagine this future. A space-based telescope observes hundreds of thousands of stars over a decade. A machine learning algorithm tracks each planet's transit with sub-second precision. It compares predictions to reality, looking for mismatches. And when it finds one, just a few seconds of deviation, it flags a possible new planet. Not because it saw the planet, but because it felt its gravity in the wobble of time. This future isn't speculative, it's already beginning. Projects like NASA's ExoMiner and TESS's data pipelines are incorporating machine learning to sort through the deluge of planetary candidates. As these tools improve, we'll be able to probe smaller systems, fainter stars, and more chaotic orbital environments. But beyond the technical, there's the philosophical. TTVs are a reminder that some truths are indirect. Just like we study dark matter by its gravitational effects, not by direct observation, we study hidden planets through the fingerprints they leave on other worlds. The cosmos is full of things we cannot see, but we can know they are real because of how they shape what we can. It's a humbling and inspiring thought that the universe leaves clues for those who pay close enough attention to the details. And the smallest details, the timing of a shadow, can tell us about massive unseen worlds. The Puli system is a symbol of this idea. A quiet star, a modest planet, a delay of 2.5 minutes, and from that, the inference of an entirely new world. How many others are out there? The more we watch, the more we'll find. But it will require a shift in how we think. We must look not just for light, but for pattern, not just for brightness, but for timing, not just for transits, but for interactions. Planetary systems are not static. They are alive with motion, with resonance, with gravitational song, and we're just learning how to listen. Someday, we may detect habitable worlds, not by observing their oceans or atmospheres directly, but by watching them pull on their neighbors, by listening to the beat of their systems, by following the rhythm of time. Puli is not alone. It told us so. Now we know how to listen.